This is a demo video for lab8, and in this part, uh, the most important issue is combine three parts of the system into a network processor. So let's look at the top view. Uh, the most important part is we need to have on a CPU to deal with a lot of instruction, and we also need to have a GPU to do some vector and before 16 add or subtract and also multiply, and so with the GPU's help we can uh, uh, do some difficult tasks. For example, if we want to implement ANN in native PGA, we definitely need to use a GPU in this project. And the convertible FIFO is also very important in lab8 because in this lab our main task is use this FIFO to combine three parts together. So let's look at some detail in the FIFO. So first let's look at the input. A total bit wide is 72 because we already have 64-bit data, the same as lab6 and lab7, and we also need to have 8-bit control. So the total bit wide is 64 plus 8. The FIFO have 4 modules. The first one is IDLE. This means we do nothing. So if we don't have any data, or we don't read, or we don't send any data, or we don't add downstage, this bit will become 00. And the FIFO out means we replay the data, and the FIFO in means that we receive the data, and the PROC means in this part we use the ARM CPU to deal with this data. And the port A is used to read and write the data. In port A we read the data from network, and we also write back some data from the processor, and so we can communicate with the network. And the port B is used to communicate with the on CPU and GPU. And this part is the uh, most basic part, because after all, although we have a lot of network processing in list FIFO, after all we are a FIFO module, so we need to have a head and a tail and a counter. So what we do is just like a very traditional FIFO, and uh, in this part it means that we are in the package capture state. IDLE also means that we do nothing in this stage, and RECV means receive. In this stage, we receive the data from the network, and down means we receive all the data, and so everything is done in this stage. So now we can see how the FIFO capture our data from network. So the most basically is uh, this one, and this one. We count our word and increase our tail, and let the address become the tail, and then we figure out which state we are. If we are IDLE, we do nothing, and if we in this stage we receive the control signal, we start to receive our data, and change our state become RECV, means we start to receive data from the package, and RECV means we already in the read stage, and if we receive a signal, means we need to change our state into the down stage. So this part is mainly for the capture data from the package, and this part is also for port A, because port A is for receive data, and also for the output data to the network, and it's almost the same. In IDLE we do nothing, and if we receive a signal, we start to change our state into the reading stage, and if we are in the standing stage, we just increase our head and do list operation, and in the down stage is almost like we restart, we reset our FIFO. We let the head and the tail become a bit 0, and also the word count also become a bit 0, and let the capture and the output stage become IDLE. In that case, we start to the beginning. So this is all the information for the convertible FIFO. This is the main focus of lab8. And the on pipeline is we use almost the same architecture in lab6. So we use the port B because port B is for the processor. Nothing very special in here. We have a five stage. It's a very classical five-stage pipeline, and we have this instruction, and this is the pipeline. So we use almost the same architecture in lab6, and then we need to use the same architecture in lab7. So as the instruction said, in lab7 we need to divide our 64-bit data into 4 parts, and each part have 16-bit data. So as you can see here, we have 4 adder and the multiplier, adder and the subtractor for this part, and the multiplier for this part we have 4. And each part deal with 16-bit data, as you can see here. And the result in the EX3 stage, we combine them together and become 64-bit data. So here we can deal with the value. It's a very simple operation in native PGA. And this is the vector. This is the adder for vector and the subtractor for the adder. And because the value and the adder and the subtractor is a little bit less complex compared to bit416 adder and multiplier. So in the GPU part, we divide the EX stage into 3 parts, and the value and the vector adder and the subtractor, we just do everything in the EX1 stage, and leave the result past the EX2 stage and the EX3 stage. And as you can see here, the bit416 is very complex. So we divide our bit416 into three stages, and just because if we just do everything in one stage, it will create a very long critical path. So we divide them into 3 stages, and do one part in one clock. And this is the multiplier. So the GPU part, we use the almost the same architecture of the classical five-stage pipeline, and the most big difference is we divide our data into four parts, and also we divide the EX stage into three parts to deal with the critical path problem. So in that case, we can combine our CPU and the GPU together and use the convertible FIFO to deal with the uh, network processing problem. So I think I include uh, some information in this part. Thank you very much.
Hello guys, this is Zhengling Wei from Team 10 in the EE533, and this is the part 2 demo for lab8, where we integrate the CPU into the network processor system building on the convertible FIFO from part 1. We have added our lab6 4-thread ARM processor and our lab7 GPU with BF load 16 tensor operations. All three share the same block RAM inside the NetFPGA. You can see here we have already uploaded our bit file and compiled it in the NetFPGA and initiated. First, let's check the system status. The mode is IDLE, which means packet pass straight through. The router is working normally. Both ARM and GPU show node running, node down. Then we will check the router function. We can confirm that the router works by ping from NetFJ to NO. The pin succeeded, so pass-through mode is functioning correctly. Now we switch to the FIFO-in mode to capture packet. I will send another ping from node 3. You can see that the one packet transmitted but the zeros received. This data show that our packet have already captured by our FPGA. Checking the status. PKT ready is 1 and PKT length is 9, meaning we have captured 4 word packets into the VRAM. Let's read the capture packet. Word 0 with control FF is the native J module header. Word 1 through 5 are the internal and IP header. Word 6 through 13 contains the ICMP payload. This is the data our processor will work on. Note, word 6 has the value. Now we run the ARM processor. This is the for lab8 quad-threaded ARM pipeline. Thread 0 runs a program that loads each 32-bit word from the packet payload, add 1 to it, and store it back. Threads 1, 2, and 3 spin. They fill the pipeline gaps, so we don't need any loop instructions. The ARM processor shows down equal 1. Looking at the result, word 6 changed in the upper half and lower half. Each 32-bit was incremented by 1. This confirms the ARM processor correctly read from the shared VRAM, process the data, and load the result back. This is the original data, and this is the result data. We can see that they are all either the upper half or the lower half. Um, they are was increased by 1. Next, we run the GPU tensor processor. It reads VRAM word 6 and 7 as BF load 16 factor for 16-bit floating point value per word and compute 3 operations. VRAM 8 holds the BF load 16 additional result. VRAM 9 holds the BF load 16 multiplication result, and the VRAM 10 holds the RLU activation result. We can verify the ReLU directly. The input vector A has four lengths. We can exactly see the result in the DRAM thing. Finally, we send the modified packet back to the network and restore IDLE mode for normal router operation. To summarize part 2, we successfully integrated three processors sharing one block RAM on the NetFPGA. The convertible by 4 captures and sends packets. lab8 ARM processor performs generally purpose packet modification using real ARM machine code, and the lab7 GPU performs hardware accelerated BF load 16 tensor operations. The priority-based multiplexer on the VRAM port ensured conflict-free access between all three. That concludes our Lab 8 demo. Thank you.